This is B. Naresh, working as assistant professor in AEC department. And today's topic is fixed bias. So before going to this biasing concept, why we go for this biasing? And we know that the transistor is acts as a amplification process here. So mean that to produce a faithful amplification by using the transistor, we need to produce a perfect biasing. So means that so the input side means when the emitter based junction is forward bias and the collector based junction is a reverse bias, then we can say that that particular biasing configuration is called as the region is called as active region here. So under the active region, the transistor is acts as your amplifier condition here. But due to the temperature condition, so beta means the current gain of the transistor and reverse saturation current of the transistor and the input voltage, the biasing voltage between input terminals, those are varies here. So if these parameters are affected here, it also affects the Q point here. If the suppose the Q point is triggers towards the either saturation or near to the cutoff, it loses the some amount of the signal of a given input signal here. So hence, to produce a faithful amplification, we require a proper biasing resistances and a proper biasing DC voltages to maintain a proper Q point in a active region here. So for these biasing methods, we have some different biasing methods here. So in that, the first one is a fixed biasing method, another one is collector to base biasing method, and another one is a self biasing method here. So in this session, we are going to discuss the fixed bias method here. Then we'll see is it suitable for design a amplification factor, amplification process or not here. So in this fixed bias, so here the base resistance is biased from the fixed voltage source here. So that base resistance here is represented as your RB here. So that is the reason. So here the base resistor is connected between the base and VCC. So here the VCC is the fixed voltage. That is the reason the base resistance is biased from the fixed voltage here. So from this case, when and we need to show that again to satisfy that the transistor is acts as the amplifier, your emitter base junction should be forward bias and the collector base junction should be reverse bias here. Then only the transistor is enters into the active region. In that active region, the transistor is acts as your amplifier here. So that is the reason. Here we are going to show that your base emitter or emitter base junction, that is a forward bias by the voltage drop across the RB. And then with respect to this biasing, it generates some flow of current. That current is represented as your base current, that is your IB here. And let us consider this fixed bias circuit here. So here I use the NPN transistor model. So means this is N material and this is the P type material and again this is the N type material. And here it is represented as a base, collector and your emitter here. And here I use a common emitter configuration here. And we know that based on the current gain parameters, and common emitter configuration is the more suitable for designing the amplification process here. So hence, here I am going to use a common emitter configuration here. And in that common emitter configuration, again, we are going to show that the transistor is acts as your amplification process here. So means that we need to show that your emitter base junction should be forward bias and the collector base junction should be reverse bias here. In this case, and if you observe this NPN transistor here, and the base is made up with a P-type material, and the collector is made up with your N-type material. So that is the reason. And this base terminal is biased with the VCC through the base resistance. That base resistance here it is represented as your RB. And here this VCC is represented as a positive polarity here. Hence, this positive DC source is biased with the base through the base resistance. So if you observe this representation, the base is a made up with your p-type material. Hence, the p-type material is a biased with a positive pole of the battery. Then we can say that that particular junction means, so which junction, your input junction means your emitter base junction becomes your forward bias. Then similarly, we need to define the collector base junction should be your reverse bias here. And if you observe the collector terminal, the collector terminal is made up with a N-type material here. And this N-type material is biased with a positive pole of the DC battery through a resistance here. And here, this resistance is represented as your collector resistance here, RC here. When we know that for a PN junction, so let us take this is the PN junction. If a P is biased with a positive pole and N is biased with a negative pole, then we can say that this is your forward bias here. And this is the P-type material and this is N-type material. If the P is biased with the positive pole of the battery with respect to your N-type material, then we can say that that biasing is called as your forward biasing here. Similarly, if the P is biased with, this is the P-type material and this is the N-type material. If the P is biased with a negative pole of the battery with respect to this N-type material, then we can say that this biasing is your reverse biasing. So that is the reason. And this is N-type material. Here, this N-type material is biased with a positive pole of the battery through a collector resistance. Hence, your collector base junction becomes your reverse bias. And based on this biasing approaches here, and we shown here, emitter base junction is a forward bias and the collector base junction is your reverse bias D. So with respect to this biasing concepts, we need to find out the operating point. So based on the operating point, we can say that either this configuration is acts as a perfect amplification process or not here. So that is the reason we are going to observe a Q point here, and we know that the Q point is a functioning in terms of output voltage and your output current here. The Q point is a functioning of with respect to your output voltage and output current. And in this fixed bias configuration, I use the NPN transistor, and this NPN transistor is a modeled as common emitter configuration here. Under this common emitter configuration, and if you want to calculate the output parameters are the output voltage and output current. So here the output terminal is a collector terminal, hence the output current is represented as a collector current. And the output voltage is measured between collector and emitter, that is represented as your VC. So hence the Q point is also depends upon the functioning of your output voltage and your output current, that is your IC, VCE and your IC parameters here. So hence first we are going to determine the Q point parameters here. So based on this Q point parameters, we need to find out that is it suitable for amplification process or not here. So from this, again, we need to find out the stability factor with respect to your temperature parameter here. So that is the reason. So first, I'm going to determine this Q point or a operating point in terms of output voltage and output current of this configuration here. So here, and with respect to this biasing, it allows the current through this base resistance. That current is represented as your base current. So here it is represented as your I. Similarly, with respect to this DC biasing, the current flowing across this collector resistance, and that current is represented as IC. And again, we need to determine a potential difference between base and emitter, that is represented as VBE. Means the VBE means the potential difference between base and emitter. Similarly, output side, again we need to calculate the potential difference between collector and emitter, that is represented as your VCE. So VCE means the potential difference between collector terminal and emitter. So this is the collector terminal and this is emitter terminal. The potential difference between these two terminals are represented by VCE here. Now, to determine this Q point, so first we need to determine, we know that generally in a common emitter configuration, IC is represented as beta times of IB plus 1 plus beta times of ICBO, or it is also called as ICO here. If you observe, means if you and where this ICBO means your reverse saturation current. If the reverse saturation current is much less than 1, we can assume that this IC is approximately equal to your beta times of IB. Means the collected current is depends upon your input current. That input current is nothing but your base current here. Means we need to identify how much base current is flows with respect to your biasing components and your biasing source here. That is the reason here I'm going to consider a fixed bias circuit here. Now, so by using this fixed bias circuit, first we need to identify how much base current is flows with respect to your biasing components, that is base resistance, and your biasing source is VCC here. To determine this IB, so I'm going to consider a input loop. That input loop is represented from base and your emitter here. So to consider this emitter loop, I'm starting from this input side loop. This is the loop for representation. So here I considered the input loop here from starting from VCC towards base resistance, towards a base terminal, and towards your emitter terminal, that is lower potential here. Hence, we need to start from the DC source. The DC, why? Because of that, your base resistance is a biased with your VCC terminal. Hence, I need to start from the input loop from this biasing source, that is a VCC, towards the base resistance, towards the base terminal, and towards your emitter terminal here. So now we need to write the KVL loop here in this base emitter loop. So starting from the source, hence we know that the VCC is equal to your. So this is the starting source. VCC is equal to, and the leaving parameters means the voltage drop across this RB is represented as IB times of RB, and this flowing towards the base terminal and towards the emitter. And in between this base and the emitter, we observe a potential drop between base and emitter, that is represented as VBE. So hence, so based on this here, I'm going to write VCC is equal to this IBRB, means the voltage drop across this base resistance IB times of RB, plus the potential difference between base and emitter is represented as VBE here. So that is the reason VCC is equal to IB times of RB plus VB. From this, we need to determine only the base current. So hence, we need to calculate how much base current is a flows with respect to your biasing components, that is nothing but a biasing resistance and your biasing source here. Hence, the IB is equal to, from this relation, the base current is represented as VCC minus VBE by RB. If you observe this one, where the VCC is the constant and the VBE means the potential difference between base and emitter, and based on the biasing concept, the VB is equal to your, the means your emitter base junction becomes your forward bias here. So when this particular junction is forward bias, it offers the voltage that is equal to your current voltage of that particular junction. So hence the VBE is either 0.7 or 0.3 based on the material. Means if we the silicon, the VBE value is 0.7. If we the germanium material, the VBE value is 0.3. Hence VB is also constant and RB we maintain the constant. Hence it allows a constant base current. From this point, this circuit is called as a fixed bias config. Means your base resistance is biased, or base terminal is biased from a constant voltage through a base resistance. So hence, so we observe how much base current is the flows with respect to your biasing components, that is biasing resistance and your biasing source here. Now, if you want to calculate the collector current, so this is the base current with respect to your biasing. If you want to calculate this IC is equal to your, we know that beta times of your IB. Now you can substitute this IB value here. So here I substituted this one. So this is the generalized formula. IC is equal to beta times of IB plus 1 plus beta times of ICB. Or we can also write in terms of this common emitter configuration, means this 1 plus beta times of ICBO is represented as ICEO, means that your output junction is your reverse bias, means your output junction is found between collector and your emitter, means that here when this particular output port is reverse bias, it acts as the open circuit, means a common, means collector and emitter, here it is acts as the open circuited. So when this collector and emitter is open circuited, it offers the reverse saturation current. That reverse saturation current here it is represented as your ICEO, or you can also write 1 plus beta times of ICBO. So here you need to substitute your IB value. So that IB is determined as VCC minus VBE by R, means the potential difference between VCC and VBE to the your base resistance, that is your RBE. Now another point is, if you want to determine the Q point is a functioning with respect to your IC and your VC. So up to this point, we identified this a collector current IC. Now we need to determine VCE here. To determine this VCE point or a Q point with respect to your voltage, and in this circuit, now we need to apply the KVL at the output side here. So that is the reason I'm going to apply the KVL at the output light or collector to emitter loop. So this is the collector to emitter loop, means the loop flows from VCC towards collector resistance, towards the collector terminal, and towards emitter and your lower potential, that is the ground, means the loop starts from VCC towards the collector resistance, towards the collector, and towards your emitter and your lower potential, that is the ground potential. So by using this output loop, we are going to write the equation. So or apply the KVL loop equation. The starting source is the VCC, hence the VCC is equal to the voltage drop across this RC, means it is represented as, so which current is the flows here? So the collector current is flows across this collector resistance, hence the voltage drop across the collector resistance is represented as IC times of RC. Again, the loop flows from collector to emitter. So in between this collector to emitter, we need to find out the potential difference between collector and emitter, that is represented as VCE. So hence, so that is VCE. So in this output loop, the VCC is equal to IC times of RC plus VC. From this loop equation, we need to determine the VCE parameter. Hence, the VCE is equal to VCC minus IC times of RC. So these two parameters, so your IC parameter and the VCE parameter to defines the Q point here. So after this, now we need to find out the is it stable or not, or a Q point is become stable or not. So why? Because of that, we know that depends upon the temperature in a transistor. The three parameters are affected here. One is the beta, means there is a current gain of this common emitter configuration here. Another one is your a reverse saturation current, that is represented as IC naught, and another parameter is your VB, input biasing voltage between base and emitter here. So now we need to find out that irrespective of these three parameters, we need to maintain a constant collector current. To provide a perfect stable condition, so we need to define the three stability factors here. So that is the reason I'm going to find out the three stability factors here. So the first factor is S, it is represented as, and this stability factor is with respect to your reverse saturation current, means the collector current is changes with respect to your reverse saturation current or beta or your the change in your VBE parameter. So why? Because of that, if the reverse saturation current is the changes, it also affects the collector current. If the beta means the current gain of the transistor is the changes, again it also affects the collector current of the transistor. If the VB is the changes, means the potential difference between base and emitter changes, so it also affects your base current. If the base current is affected, the collector current is also your affected here. That is the reason. Based on these three factors, we are going to find out the stability factors here: S, S dash, and your S double dash here. To determine this S, the S is depends upon the rate of change of collector current with respect to the rate of change of your reverse saturation current by making another two parameters are constant. So what are the two parameters here? Beta and your VBE. So that is the reason we are going to maintain beta and the VBE is a constant. Now we need to observe how much collector current changes with respect to your change in reverse saturation current. So hence the S is defined as, for this case, I consider this same circuit and I'm going to consider the generalized expression for collector current. The collector current is represented as beta times of IB plus 1 plus beta times of IC naught, ICBO or IC naught here. Both are same, the reverse saturation current here. And in this, I'm going to calculate the stability factor S. This S is defined as the rate of change of collector current is changes with respect to the rate of change of reverse saturation current here. To observe the stability factor, I'm going to differentiate this collector current equation with respect to your IC. Hence, I'm going to apply the differentiation, the above equation with respect to IC. If you apply the differentiation, dou IC by dou IC becomes your 1. So 1 is equal to, this is beta times of dou IB by dou IC plus 1 plus beta times of dou IC naught by dou IC. So hence, this equation is differentiated with respect to your IC. Hence, dou IC by dou IC becomes to 1. And this is beta times of dou IB by dou IC plus, and again differentiate with respect to IC means 1 plus beta times of dou IC naught by dou IC. So by using this mathematical relation, now we are going to find out the stability factor. So stability is defined as, it is the rate of change of collector current with respect to the rate of change of reverse saturation current by making beta and VBE is constant here. So means that we need to find out this ratio dou IC by dou IC naught. For this case, simplify this mathematical relation means what happens here? Just take this outside here. So this is 1 minus beta times of dou IB by dou IC, that is equal to 1 plus beta by dou IC naught by dou IC, where dou IC naught means reverse saturation current and IC means your collector current here. So here, what we required here, dou IC by dou IC naught is required here. Hence, by using this relation, I am going to calculate dou IC by dou IC naught, that is equal to 1 plus beta by 1 minus beta times of dou IB by dou IC. And we know that this dou IC by dou IC naught is represented as your stability factor S. So hence, the stability factor is represented as S is equal to 1 plus beta by 1 minus beta times of dou IB by dou IC. So by using the stability factor, we need to find out that this fixed bias is suitable for to design the amplification process or not by using the transistor. So how we can say that is the best amplification biasing means that when the stability factor is approximately equal to unity factor, then we can say that that particular biasing is suitable for to design the amplifier by using the transistor here. So based on this fixed bias configuration, now I'm going to calculate how much stability factor is offered by using fixed bias here. So let us consider the stability factor. S is defined as 1 plus beta by 1 minus beta times of dou IB by dou IC. In this case, so where 1 and beta is a constant, now we need to find out the rate of change of base current with respect to the rate of change of collector current here. From this fixed bias, we know that the base current is represented as, it is a ratio of the potential difference between VCC and the VBE to the base resistance. So IB is equal to VCC minus VBE by RB. For this base current, we need to apply the differentiation with respect to your IC. Hence, just apply the differentiation with respect to your collector current for this base current. So what happens here? Where the VCC is the constant, VBE is a constant, and the base resistance is also constant. We know that the differentiation of the constant is 0. Hence, dou IB by dou IC becomes 0. Now I can substitute this dou IB by dou IC value in this stability factor. Now what happens here? So this is 1 plus beta by, we know that S is equal to 1 plus beta by 1 minus beta times of dou IB by dou IC. And we observed here dou IB by dou IC, that is equal to 0. Hence, S is equal to, this is 1 plus beta by 1 minus beta times of dou IB by dou IC value is 0. Hence, S becomes to 1 plus beta here. In this represent, by using the stability factor, and this S is equal to 1 plus beta. And we know that for the common emitter configuration, beta value lies between 50 to 500 here. At least the minimum value of current gain of the common emitter configuration. For this fixed bias, the stability factor shows that 51. Why? Because of that, beta lies between 50 to 500. If I consider the minimum value of the current gain of this common emitter configuration, in this fixed bias, the stability factor means that is 1 plus beta, means S is equal to 1 plus 50, that is nothing but a 51. But we know that when stability factor is nearer to the unity value, then we can say that that particular biasing is the more suitable for design the amplification process here. That is the reason this fixed bias has some disadvantage. What is the disadvantage? It contains more stability factor here. Now, to determine this S dash, again, let us consider the collector current. IC is represented as beta times of IB plus 1 plus beta times of IC naught. And for this, we need to define your S dash. So here the S dash is defined as, it is the rate of change of collector current with respect to the rate of change of VBE by making beta and IC naught is constant. So hence, to differentiate this collector current with respect to your IC here, and here, so here I substitute this IB value. IC is equal to beta. What is IB value we observed from the fixed bias? That is defined as the ratio of the potential difference between VCC and the VBE to the RB. This is the IB value, VCC minus VBE by RB plus 1 plus beta times of IC naught. And for this, I am going to differentiate this with respect to your IC. Now what happens? Dou IC by dou IC becomes to 1, and where VCC is a constant and VB is not constant. Only to determine this S dash, we need to consider beta and reverse saturation currents are constant. S dash is represented as the rate of change of collector current with respect to the rate of change of your VB. So that is the reason. So for this, you can apply the differentiation. What happens here? This is minus VBE by dou IC, and this RB is a constant. Again, IC naught is a constant, hence the differentiation of the constant becomes your 0. So hence, after this differentiation with respect to IC, we got this 1 is equal to minus beta times of RB times of dou VB by dou IC. From this, we need to derive this S dash. So what is S dash here? S dash is represented as dou IC to the dou VB. So if you define from this the S dash, so now what happens? This is 1 by S dash. So hence S dash is equal to minus beta by RB. And similarly, if you want to calculate S double dash, so S double dash is defined the rate of change of collector current with respect to the rate of change of current gain by making VBE and the reverse saturation currents are your constant. So hence again I consider the generalized expression of the collector current IC is equal to beta times of IB plus 1 plus beta times of IC naught T. For this expression, I am going to differentiate with respect to your beta. So what happens here? Dou IC by dou beta becomes, so this is with respect to your beta means, so this is IB plus, this is 1 plus beta times of IC naught means, if you derive this, if you expand this equation, IC is equal to beta times of IB plus IC naught plus beta times of IC naught. If you identify this S double dash, we maintain that VBE and IC naught is a constant. We assume here means, so here the IC naught is a constant means the constant differentiation is 0. So here this is beta times of IC naught. So we are going to differentiate with respect to beta. Hence this value is equal to IC naught. So hence dou IC by dou beta, that is equal to IB plus IC naught. So up to this point, we observed the biasing configuration, fixed bias configuration. In that, we identified the Q point parameters with respect to your output current and your output voltage. Then we also identified the stability factors, that is S, S dash and S double dash here. Out of these three stability factors, S is the most important here. So based on the S, we can identify that biasing configuration is suitable for to design the amplifier by using the transistor. But in that fixed bias configuration, we identified that S is represented as 1 plus beta is not nearer to your unity factor. It is always greater than of unity factor. This is the major disadvantage of fixed bias circuit. So in the S double dash, we observe that the S double dash is represented as IB plus IC naught, where the IB is represented as base current and IC naught is represented as your reverse saturation current. And we know that the reverse saturation current is always much less than of your input current, that is IB. Under this assumption, S double dash is represented as only IB. Now we'll see the one problem here by using this fixed bias. So let us consider in a silicon transistor circuit with a fixed bias, VCC is a 10 volts, RC is a 4 kilo ohms, RB is a 930 kilo ohms, beta is a 100 and the VB is 0.7. Solve the operating point and stability factor. This is a fixed bias circuit, and in this fixed bias circuit, they given that the base resistance, your RB value is 930 kilo ohms, RC value is 4 kilo ohms and the VCC value is 10 volts. Then beta, that is the current gain of for this transistor is 100. VB is 0.7, means that this transistor is made up with a silicon transistor. So by using these parameters, we need to find out the operating point. And we know that the operating point or the Q point is a functioning with respect to your output voltage and output current, that is VCE and IC. So means that we need to calculate IC parameter and VCE parameter. So from the fixed bias configuration, we know that the base current is a represented means, so this IC is represented as beta times of IB plus 1 plus beta times of ICBO. So if reverse saturation current is a very small compared with your input current, IC is approximately equal to beta times of your IB. If we want to determine this collector current, first we need to identify that how much base current is the flows with respect to biasing components here. And from this fixed bias, we know that the base current is represented as it is a ratio of the potential difference between VCC and the VBE to the base resistance, that is RB. So if you observe this relation and based on the given statement, they given that VCC value, VBE value and RB value. From the problem statement, VCC they given that 10 volts, VBE is 0. 0.7 and RB they given that 930 kilo ohms. So means we can substitute all these values here. So VCC is the 10, VBE is the 0. 0.7 and RB value is 930 kilo ohms here. So hence IB is equal to 10 minus 0. 0.7 divided by 930 into 10 power 3 or K. So after this, you can solve this ratio. It gives that IB is equal to 10 microamps here. So mean that is equal to 10 microamps. Now by using this base current, now we can calculate how much collector current is offered by using fixed bias circuit. And we know that IC is equal to beta times of IB. In a problem, beta they mentioned that 100. So hence beta is equal to 100 and we observe this IB is equal to 10 microamperes. Now we can substitute these two values in this collector current expression to observe how much collector current is the flows by using this fixed bias circuit. So hence IC is equal to, where beta is 100, IB is equal to 10 micro, means 10 into 10 to the power of minus 6. Then you can solve this one. It gives that the collector current is 1 milliampere. So from this, from the based on the given statement, we observe that the collector current is 1 milliamperes. Then to define the Q point, again we need to calculate the output voltage based on this configuration. We need to calculate VCE. So to determine this VCE, we know that from the fixed bias, VCE is represented as VCC minus IC times of RC. So in a problem statement, they given that VCC value, IC we observed here, RC also they given. Now we can substitute this VCC and the collector current and the collector resistance values here. So VCC equal to 10, IC we observed 1 milliampere, RC they given that 4 kilo ohms. So this milli and K is the get cancel. 1 into 4 is 4. So 10 minus 4 is nothing but 6. So that is the reason VCE is represented as 6 volts. So up to this point, we observed that IC and the VCE. If you want to define the Q point is a functioning with respect to your collector current and output voltage VCE. So hence IC we got that 1 milliampere and output voltage we got that 6 volts. These two are defines the Q point, hence it is also called as the operating point. And from this, the operating point is represented as the Q is functioning of VCE comma IC. So where the VCE we got that 6 volts and IC we got that 1 milliampere. Hence these two are defines the operating point or also defines your Q point. The Q point values are 6 volts and 1 milliampere. So again in the problem they ask you the operating point as well as your stability factor. So to define the stability factor from the fixed bias, we know that from the fixed bias configuration, the stability factor is defined as 1 plus beta. And in the given problem statement, the beta value is 100, hence the stability factor is becomes S is equal to 1 plus beta is replaced with 100, hence your stability becomes 101, 101 here. So up to this point, we observe the operating point and the stability factor for a given problem here. So the operating point is 6 volts, 1 milliamperes. And the stability factor is based on the given statement, the stability factor is 101 here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.